Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about two very important topics, Central Limit Theorem and confidence intervals. Very important, you will see these topics coming again and again in across machine learning and across statistics also. Okay, you will see it again that's because of Central Limit Theorem, this and that. Even in my previous videos, I have discussed about that. And today we'll discuss about that in detail and understand all the underlying concepts for that. So the things which we need to understand before diving into Central Limit Theorem are sample mean and population mean. I have discussed about this also earlier, but I'll again make it very clear. Then law of large numbers. In my previous videos, I have discussed about weak law of large numbers and strong law of large numbers. I'll put the link of those videos also in the description. And then we'll proceed to basis of this. On the basis of these understandings, we'll understand what is Central Limit Theorem. And then we'll discuss a small topic within this, that's standard error. We'll understand that too. And then we'll move to confidence intervals, very important again. So let's go one by one. So first thing, population mean. What is population mean? What does population mean here? When we say population, what do we mean? What do we understand? Population is the entire group that we are talking about in terms of statistics. So for example, if I want to calculate the average height of a city, of people in the city, then the population will mean the population of that city. But if I talk about the population, average height of the people in a country, then the same population will mean the entire population of the entire country. So that's what, depending upon the context, the population will differ. If I'm similarly for a much smaller sample size, for example, if I'm doing the average height of a class of class of students of some standard 10, okay, standard 10. So that will be my population, but I won't measure each and every. I'll take a sample out of it, okay. But I hope population is clear. Depending upon the context, the population size will vary. So let's define it. So that implicitly means the entire group that we are talking about. That's our target group. So true average mean means average. True average of entire group. So it tells me the central tendency of the entire population. So it gives me the central tendency of entire population, which is the balance point, which is the central, which is the representative point. Okay. So that's what. So the formulation, how do we do is it's denoted by mu, and it is 1 by n. N is the total number of data points in the population, and then sum all the data points that I have, xi. So here my xi n would be number of data points in population. So that's my n. Similarly, but generally we cannot get each and every person's height in a city or in a country, more difficult. So what we do is we go with the sample mean. We collect a small subset out of these people or the group, and that we take as a representative. That's what we mean by sample. We take a subset of that complete group, and that's what is a sample. So this is average of smaller, that is smaller than that, a representative subset of the entire population. This is the average again. We are talking about mean means average. Average of a smaller representative. We're taking it from the same city. I'm taking not the entire city's population, each and every person, but a small representative subset. Okay, representative subset, and that is called a sample of the population. That is the representative of the population in any case. Okay, and this provides an estimate. This provides an estimate because we can't go for each and every data point in the population, so it provides an estimate of population mean. So this is an estimation. Even if we don't have the exact value, this sample will give me the estimate. I hope these terms are clear. So this is represented by, this was mu, and this is represented by x bar. X bar is equal to 1 by n, sigma I equal to 1 to n xi. And similarly here also, n is equal to number of data points in sample. Number of data points in sample. So once we have these two defined, we have the understanding, right? What is a sample? This is a smaller representative set of the same population, because we can't have all. This is practically very difficult or kind of impossible to get all the data. So we go with the samples, and that's how we do statistical approach. So for this sample mean, this is the basis of all the calculations we do. And for that, we have what we call as law of large numbers. This is the law, very important law, which tells us that as the number of, so this is the number, right? This n, this is a smaller representative subset of the population itself. This sample is a smaller representative subset of the population itself. As n grows and grows, so at some point, as n tends to infinity, this sample will become the population. This number of, if I collect all the data points from the population, so as n tends to infinity, definitely all these data points and will become the population. This n will tend to this capital N, right? And that's what this law of, and this my sample mean will become my population mean. And this is what my law of large numbers says, that if n, because this is a small representative set, n is very, very large. For example, if I am taking the even the population average height of a city, so I will take not every but very small samples from different localities, and I'll take the average height of that. Even for like if we do this what do they make predictions of results, right? Exit poll. So that time also they do take small samples from the representative, and they make predictions based on that for the entire population, that how the entire population will vote. So that's the same logic we apply. So law of large number states that as the number of IID, as the number of these samples, as the number of IID samples. So IID we have discussed in the past. IID is independent and identically distributed. Independent means each sample is independent of each other, with one another. One sample does not influence other. And identically distributed means they are coming from the same kind of distribution. So as the number of IID samples from a population, I'm talking about samples from population, increases, then as it increases, their sample mean, whatever I have discussed, I am just writing it. Their sample mean will or converges to the true population mean. Mu. So as this number of IID samples n, say tends to infinity, that it goes bigger and bigger, very large. Okay, so as the number of IID samples from a population increases, so the number of samples that we are collecting here, as this small n increases, the sample mean x will converge to the true population mean, and that's what we understood. So this sample mean is x bar, and this is mu. So as this samples, if it increases to the true population, definitely it will go. So as it goes towards this, as it grows larger and larger, the better our estimate becomes, and it converges, it becomes very close to the population mean. This is what law of large number says. This is the basic for all the sample collection, for all the statistics. I hope this is clear. And now on the basis of this, we define what is central limit theorem. So let's understand the central limit theorem. Very important. Central limit theorem. So again, central limit theorem for any sequence of IID random variables. So for any sequence of IID, again random variables, I have a sequence of random variables IID, okay, with finite mean and variance. So the mean and variance of that should be finite, whatever sample I have. Okay, the mu, mean, and the sigma, variance, sigma square. they should be finite. Okay, so the distribution, though I have collected many samples, so as this sample there are many samples are there, so as the this n increases, right? So the sample means the sample, I'll collect my multiple samples. Say for example there are one sample x1, x2, x3, there are multiple samples like this xn. So each sample will have x1, x2, x3, sorry, x3, small x, xn within that, and then x11 like x12, x13 like that, x1n, and this will have x21, x22 like that till x2n. So they all are having nn samples, okay, and each one will have, say this is x1 bar, this will give me x2 bar, and similarly this will give me xn bar. Okay, so I have these n samples, each one has these many, say n is 100 here. So I have these IID random variables, and within that each sample I have say n equal to 100, and I am doing this multiple times. So this is one. So I took one sample of 100 people for I am calculating the average height of a city. I took one sample of 100 people, I found the average height. I took the another sample of 100 people, I got average height as x2 bar, and similarly I did it n times, okay, and I got, or say for example, I don't confuse, I'll do it k times, okay. This is a n here, so this n and this is different, so this will be xk bar. So this is my n, okay, this is the n I'm talking about, this is my sample size n, okay. So let's be very clear, this is my n sample size, this is my sample size, this is sample size, okay, and I have k such samples, and I'll get k such means. And now central limit theorem says that if I plot these means, whatever is the distribution they are coming from, okay, whatever the distribution they are coming from, central limit theorem says that if I plot these means, they will follow a Gaussian distribution. So these means, okay, will follow a Gaussian distribution. The PDF of this mean will be a Gaussian. This is what central limit theorem says. I hope that is clear. And irrespective of whatever the distribution, underlying distribution it is, it doesn't matter whether these samples they are coming from a Bernoulli or a whatever unknown or some random sample, but the means, they will follow a Gaussian or a normal distribution as n becomes very large. So that is one of the law of large numbers. So as n, for very large n tends to infinity, or for very large n, okay, for very large n, these all sample size, this is sample size n equal to 100. Okay, for very large means for all practical purposes, what is large n? N should be at least greater than or equal to 30. Below this, n is considered small. So n should be greater than or equal to 30 to be considered large. If n is greater than 30 for each trial, okay, if I have at least 30 samples, then this will be considered as a large sample. And then if I plot these means, I will get a Gaussian distribution. This is what is central limit theorem. I hope this is clear. Okay, and let's formally write it and understand some more things around this. So if central limit theorem is clear, so it talks only about the distribution of means. This is the distribution of means, distribution of sample means, to be very clear, sample means for large n is greater than or equal to 30, and this is a Gaussian. Okay, so this is the distribution of, this is the PDF. So these means, whatever we calculate, okay, so there will be one central this will be a population mean, and then there will be, this will coincide with x bar will become mu equal to mu at the center, and then all these means that we calculate for each of these trials, they will be under this Gaussian. Okay, so now let's formally write it. in mathematical terms also, and do some maths on that to understand what is the next topic, that is standard error. So let's write x1, x2 like that, xn as I mentioned earlier are IID random variable. Okay, and so let me let me write that also. Okay, so these are random variables, and with a finite mean and variance, finite mean mu and finite variance. Okay, let me write it, finite variance also. And so I have, for a sequence, so I have these random variables. So now for this, for given this, the distribution of sample means will be Gaussian. And what will be the parameters of that Gaussian? So I'll just come to that. Okay, Gaussian, and this will be, generally I write it here, sigma square by n. So the mu will be the mu, as I mentioned here. This will be the mu, and the variance of this will be sigma square by n, not sigma square. Sigma is the data variance of the data, but the variance of this mean will be sigma square by n, and we'll prove that. And this is our standard error. This is called standard error, the standard square root of this. Okay, the standard deviation of this. And why the distribution will will be a Gaussian irrespective or regardless of the original population from which these samples are collected. These samples, population distribution, whatever is the distribution of these x1, x2, these sample means will follow a Gaussian. I hope that is clear. And now let's derive this. How is this variance? Sigma square by n. So again, as it is mentioned here, let's do. So x1, x2 and IID. So what will be the mean of this? So the mean will be expected value of xi, that will be equal to mu, that is the population mean, for very large number. That's what law of large number says. And then what will be my variance? My variance would be variance of xi. Xi is, what is xi? Xi is from here, x1, x2, xn are IID random variable, whatever, I don't know the distribution. So this I is coming, I will vary from 1 to n. This is I, and these are IID, independent and identically distributed, coming from the same kind of distribution. So this is the variance. Now, what will be my xn bar? The sample mean of all of this. So this will be 1 by n, sigma I equal to 1 to n xi. So this will be equal to 1 by n x1 plus x2 plus x3, so on till xn. This will be my sample mean. Okay, this is your population, this is your sample mean. And now I want to calculate. So this is coming, just watch carefully. This xi is denoting this data that we collected. This xn bar is the mean of this data. This is the sample mean of this data. Xn bar. This is the sample. This is what I'm using. Okay. And now if I want to calculate, so what? And I'm saying that this mean will follow a Gaussian with mu as the mean, and the variance will be this. So we know by law of large numbers that the sample mean will converge to mu as n grows large, that we know. And now the second part we have to calculate. By law of large numbers, the sample mean will converge to mu. That's what we saw here, law of large numbers. X bar converges to population mean. And now the second part is how the variance becomes sigma square by n. Let's do that. So how will we write variance of xn bar? This is your, not I, this is not xi bar. Variance of xi, this is equal to sigma. This is finite, less than infinity. Okay, this means that this is finite. Variance is sigma square. Sorry, sigma square. Okay, so we have, so variance of xi is sigma square. The underlying data, whatever is there, we can compute that, and that is finite. I want to compute the variance of the sample mean now. Okay, variance of the sample mean, what it will be. So for this, we have to calculate two things. This will be equal to, we will apply two known theorems. This will be equal to variance of, and then we'll put these things 1 by n, and this whole thing x1 plus x2 plus so on till xn. Okay, this is what it is. Xn bar is the average of all these, and I want to calculate the variance of this. So the two things we know already. We will, in the past, first thing is variance of x plus y is equal to variance of x plus variance of y, because covariance xy equal to 0. There's one more, plus 2 times covariance of xy here, but this is equal to 0 because the assumption is IID, independent, and as soon as two variables are independent, the covariance becomes 0. We have seen that, we know that already, multiple times we have seen. So variance of x plus y is variance of x plus variance of y. What is the second thing? This is simple, you can do variance of some constant times c of x is equal to c square times variance of x. So this is a constant, and variance is all square terms. It is all the terms are squared. So this c, if you multiply with every term, so this c square will be multiplied with the variance. You can check it with a simple example and you will get this. So these are the two things. Now based on these two things, we'll recompute what this comes to be. So now this is equal to, now again we know that variance of, I want to compute this is equal to variance of 1 by n x1 plus x2 plus so on till xn. Okay, and now 1 by n is a constant, so this will come out, and what we know, c is c square, the constant times will come out, so this will be equal to 1 by n square times variance of x1 plus x2 plus so on till xn, and this will be equal to variance of x plus y is equal to variance of x plus variance of y. So this we can split it out separately. This will be equal to variance of x1 plus variance of x2 plus so on till variance of xn, right? This is n square. Okay, let's not miss the term. And we know that variance of any xi for the sample is equal to sigma square. Yes, we have put this for any I, the sigma square. So for each of the terms, we'll have sigma square plus so on till sigma square for each term. This will be n times for each of the term, n times for each of them. The variance is sigma square, same, because that is coming from the same sample. Next, so we can write this as 1 by n square into n times sigma square, because this is n times this n square goes. Okay, so this will be equal to sigma square by n. So variance of sample mean is equal to sigma square by n, and that's what we proved here. This is the Gaussian. So the Gaussian final, the distribution of sample mean will be a Gaussian with mu and sigma square by n. Mu is the population mean, and this is the sigma square is the variance of the sample divided by n. N is the number of, this is the sample size. This is the sample size. I hope that is clear. Okay, and what is the next point? So we know that standard deviation is equal to square root of variance. Here, what is the variance of? So similarly, standard deviation of the sample mean. What will be the standard deviation of xn bar or sample mean? This will be equal to square root of sigma square by n. This will be equal to sigma by square root of n. So this variance of the data was sigma square. So standard deviation of the data will be the standard deviation of the data here only. I'll write it. So standard deviation of the data would be square root of this. That will be sigma. But the standard deviation of the sample means is sigma by root n. And this in our context is called as standard error. This is also called a standard error. This is equal to sigma by root n. That is the standard deviation of not the data but the sample mean, whose distribution is mu and sigma square by n. Variance is this. So the standard deviation of the sample means is known as standard error, that is given by sigma by root n. I hope that is clear. So the standard deviation, I made it very clear. Again, let it be very clear. Standard deviation of the population is coming, that is sigma. Standard deviation of the data that we have, IID random variables, that is given by sigma. And then we calculated the sample means, and that sample mean follow a Gaussian because of Central Limit Theorem, whose mean is mu and whose variance is sigma square by n. And the standard error is given by, and the standard error is the standard deviation of the sample mean that is coming from the Gaussian here. I hope standard error is clear. Okay, and for making it more clear, so let's do a concrete example and then we'll move to standardize. Okay, let's standardize it also. Okay, standardize sample mean. So let's standardize. So what is standardizing any random variable? Standardize any random variable y is equal to, what do we do? Yi. So when we standardize this, what do? We do whatever is there, each value in yi, we subtract the population mean and divide it by the population standard deviation. This is also called mean centered standardization, means mean centered and variance scaled. So scaling factor is variance. Variance is standard deviation, that is square root of variance. So mean centered, I'm centering it towards the mean and I'm scaling it by the factor 1 by square root of variance, that is my standard deviation. This is my scaling factor is 1 by sigma. And for each of the data in the sample, each of the, there will be x1, x2 like that till xn, right? Or y1, y2 till yn. So each of the sample, so instead of x, I should write yi here to make it, so avoid the confusion. So this will be yi minus mu y, whatever is the population mean of that, and this will be sigma y. So this is mean centered. So if you take anything, right, this will make it okay. The mean will become 0 and the variance will become 1 because of this. And if it is Gaussian, if it is coming from Gaussian, then this will become a Gaussian with mean 0 and variance as this will be mu and sigma. Mu is equal to, this is mu and this is sigma square because of the standardization. You can take any simple example, just play around. So let's say 1, 2, 3, this is sample, this is the mean, right? If I subtract the mean from each one, I'll just show you the mean centering part. Okay, so subtract from each of the data point, I have 3 samples. This will become, after mean centering, will become 1 minus 2 is minus 1, 2 minus 2 is 0, and 3 will become 1. Now what will be the mean, new mean of this? This will become 0. The mean of this will be 0. Similarly, you can calculate the standard deviation and then divide it by standard deviation. So automatically standard deviation will become 1. So this is what it does. It will move the mean to 0 and standard deviation to 1. This is called mean centered and variance scaled. I hope this is clear. Standardize it. Why am I doing this? So just standardizing and showing you to give you one more information around this. So anything Z is the symbol for Gaussian. Okay, Gaussian here. Zn is equal to. So I'm standardizing my this thing. Sample mean. Standard. Okay. So I have standardized sample mean as xn bar in the sample mean minus mu. And what is the samples standard deviation? Variance of xn bar. Square root of this is standard deviation of that. That is our standard error. This is also called standard error. This is equal to standard deviation of sample mean. I'm just repeating the point so that it becomes very, very clear and you don't forget this. So this is your 1 by n sigma I equal to 1 to n xi whatever by mu, and this will be sigma by root n because that was sigma square by n. And this, after standardizing, we say that d will tend to a normal distribution or a Gaussian distribution 0 to 1. And what does this d mean? So this d means, this d denotes convergence in distribution. Convergence. We discussed convergence in probability and in the previous video also. I'll put the link in the description. Convergence in distribution. So this is another type of convergence. Okay, so this d means after this is standardized, this will converge in distribution to normal or a Gaussian distribution with mean 0 and variance 1. And also this will, when will this converge? As n tends to infinity. Then we have more and more data sample, because then this will become 1. Both will become same and this variance will become same. Okay, 1. So we have discussed what is standard error. So I hope standard error is clear. Okay, and let me demonstrate again whatever I have mentioned earlier. What does central limit theorem say in a concrete way? Whatever I have discussed earlier. I'll give you one more example so that it becomes very clear. What is sample and what are this? Okay, so the city example only. So let's collect the height of people in a city. Okay, and let's say the size of each sample is 100. So n is equal to 100 is my sample size, and I'm collecting height of people. And then let's repeat this collection 1000 times. Okay, so let's repeat this. K is equal to 1000 times concretely. Okay, so I have one sample which has 100 heights of people, and I calculate the mean of this. Okay, so let's say that this is x1, which has x1, x2 like that till x100, and from this I get one x1 bar, x2. Similarly, this is 1, 1, 1, 2 like that till 100 like that, and similarly for x2 this will be the sample. From this I get x2 bar, and like this I have xn, and again this I have 100 samples and I get xn bar. Okay, and now if I take, okay, if I have now k data points here. Sorry, these are k. Okay, k, or this will be 1000. K is 1000 here, right? So n is equal to 100. This n is 100, and this k 1000 times. I'm repeating the sampling 1000 times, 1, 2 like this 1000 times. Now I get 1000 data points, and now I have plotted these 1000 points. I will get a Gaussian. That's what I meant. This will be a Gaussian with some mean, and some mu will be mu, and then sigma square by n will be its variance. I hope that is clear. K is the number of repetitions, and we have to do this k number of times because only then we can plot it. Otherwise, if I just have one sample, what will I plot and what will I get? This is one data point. I will get some 1000 data points, only then I can plot this, right? So there will be some data points which I will get here. So for that I am doing it k number of times so that I can find out what is the plot like. Generally this will be histograms. one value, and from that we can take the tips and we plot it, and then we'll see that okay, this is a normal distribution. We plot it as histograms. I hope this is clear now. Now let's move to the next topic, and the last topic of today, very interesting, confidence intervals. So we use this central limit theorem and calculate confidence intervals. So what is the confidence interval? It gives me, so generally when we calculate a mean here, right, from a sample, we get one point value, single point. But what confidence interval, sometimes it is difficult to get a concrete 1 point value. So generally in scientific papers, in medicines and etc., right, you will see the confidence interval, because that is more accurate way of representation than just one data point, because one data point can be misleading. We can have a lot of outliers, and then you can just manipulate the data and show something, that what is the mean of some data that I have done, mean improvement time or whatever, what is the mean performance, etc. So you can have some outlier data performance, and from that, so because of that, we use confidence intervals, which is a better or more accurate representation of the actual mean. And that's a utility. Instead of giving 1 point value, give me the range of value with the confidence level, that how much confidence you can say that the population mean will lie in this range. Okay, and that confidence level can be 50%, 90%, 95%, 99%. Generally 95% is the common thing which is used everywhere. So confidence interval by default, mostly it's 95%, but we also see 99% or 90% confidence intervals. And I'll also explain what does this confidence level mean. So what is confidence interval? Range of values that is likely to contain my true population mean. This gives me the range of values that is likely to contain our true population mean. Instead of 1 point estimate, I am giving a range of values. This is a better, more accurate representation. Okay, so instead of giving a point estimate, I'm giving a range of values. Instead of giving a point estimate, as we saw in the sample mean. Okay, it gives a range of values with confidence level. What does confidence level mean? For example, if I say that I have 95% confidence interval, does this mean that there's a 95% probability of finding for example, if I have some population mean, right? So I'll give you one range. For example, average life expectancy. If I say that it is between 75 to 79, say this is my average, very tight, 75 to 79. Okay, so I say this. So does this mean that there is 95% chance of finding the true average life expectancy here? No, because the average life expectancy would be some number. Say for example, that will be 77.2 or something. Okay, that is my average life expectancy. Okay, average life expectancy. So I say that with 95% confidence that this will be so this is 1 point, and I cannot say that there is a 95% probability chance. Okay, with 95% probability, the chance of it is that it will fall in this range. The probability, okay, we give it for a probability distribution. For example, if I have a Gaussian like this, then I can say that if I have two values here which are plus minus 2 standard deviation away from on both sides, then I can say that my data will lie in this with 95% confidence interval. But only if my average life expectancy is a PDF. It's a distribution, but this is one value. So this is one value. This doesn't mean that this is a probability. Means with 95% probability, I can find it in this range. This is plus minus 2 standard deviation away from the mean, and I can find that way. So it doesn't mean this. Okay, so what does this mean? Let me give you an example, and there is a slight difference, and then you will understand this. Okay, so it means that if we repeat the sampling process, many times, then 95% of those calculated intervals will capture or include the true population mean. So if I do it multiple times, say for example, if I'm capturing the mean, I'm doing this 100 times, so 95 times of that 95 confidence intervals will have my 77.2, and five confidence intervals may miss or may not include this 77.2. Either they may be less than this or they may be more than this. For example, if I have a confidence interval for this which is 72 to 75, this doesn't include 77.2, right? So I can have 5 such samples which is missing this. Or for example, I have one confidence which is like 78 to 81. Okay, so again this is higher than 70, so this is missing this, is not having this. So I can have 5 such samples. If I take this 100 samples, so I can have 5 such confidence intervals which may not include my true population mean. That's what 95% confidence interval means. That if 95% in the long run, I'm telling 95 out of 100, but it will be in the long run. If I do it multiple times, then 95% of those calculated confidence intervals will include my true mean, true population mean. I hope that is clear. Let me give you an example. For example, let's say we are measuring the weight of some variety of dog, okay, some certain species of dog. So I'm trying to measure the true population mean of a species of dog. True population mean weight of a species of dog, and say that is 30 kg. We know this. Okay, we know this. And we have to see that the measurements that we are doing, whether using the confidence interval, whether we are getting it or not. Okay, so we want to estimate. We want to. What is the goal? Task or goal is to estimate mu. That is the population mean. Okay, using 95% confidence interval. Okay, let's see how we will do it. So say for example, I have a sample number, okay, and then the sample mean, that is x bar for that, and then I have 95% confidence interval, okay, and then whether this confidence intervals has this, okay, does it have, or does it capture mu, question mark. Okay, so this is 30 kg. We know this is not 36. Okay, so this is 30 to make it clear. So let's see. So what are my samples? So sample number 1, for example, sample mean is 29.8 and the confidence interval here is 28.5 to 31.1. So does this have my 30 kg? Yes, this is lying in this confidence interval range. So here I will say yes. Okay, so later on I'll do this too. So second one is 30.4 and the confidence interval here is 29.1 to 31.7. That is 95% confidence. And the third one is 31.5, where this is 30.2 to 32.8. Okay, and then there's a fourth one which is saying 28 kg, and this is on the lower end, that is 26.7 to 29.3, and so on, like this we have till 100. The 100th one is, say for example, this is saying the sample mean is 29.9. everything is in kg. Okay, kg, and this is also, the range is also in kg. Okay, this is selling that 28.6 comma, this is from 31.2. okay, so does this have 30 kg? Yes, this one also has, yes, 30. No, this is greater than 30, right? It just missed 30 by just. This is no, this is no, and again this is yes, yes. So if you see, this has 30 kg, this confidence interval has 30 kg, because this is 28 30, 29 to 31, this has 30 kg, This range has 30. 30 to 32.8, it is just beyond 30. So this has missed 30. So this doesn't capture. This confidence interval doesn't capture. Similarly, this 29.3 is the higher end. This has just missed 30 kg. So this confidence interval also doesn't capture my actual population mean. That is mu. This is my mu. So what I am saying is that 95% confidence interval means that 95. So if I do it in the long run, right, 95 out of 100 such samples will have true population mean, and 5 samples may miss. Okay, may miss. They may, like, these 2 samples don't have this. Similarly, 5 samples may miss to capture the accurate true population in the given range. That's what 95% confidence interval means. I hope this is clear now. Okay. So for normal distribution, so let's see, give me your formula for normal distribution. So for normal distribution, what do we do? What is the formula for normal distribution? Normal or Gaussian? Both are same. Normal is Gaussian, and you just keep on repeating so that it gets into your head. Normal. So we know that the rule 68, 95 and 99 rule. So there's 95.4 and this is 99.7. But okay. So this is this is plus minus 1 standard deviation. This is plus minus 2 standard deviation. This is plus minus 3 standard deviation. So the data will lie between, if I have this mean again, if I do this bell-shaped curve, and I have, say this is the mean, and say this is 1 standard deviation, like this, 1 standard deviation. This is minus 1 standard deviation. This is plus 1 standard deviation, this side. So my 68% of my data okay, 68% of my data will lie here. That is 34% here and 34% on the other, because this is symmetrical. This is minus 1 sigma, this is plus 1 sigma. Similarly, if you go minus 2 sigma till plus 2 sigma, and then this will be plus 3 sigma here, and this will be minus 3 sigma. So till here, this value will become 95, this complete graph, and then till here it will become 99. What is this captured? And this is a PDF, right? So this PDF will be equal to 1, or that will be like 100%. But this is very useful to understand. Okay, I'll just reiterate this. Okay, so what is the formula for confidence interval for normal distribution? So my CI is equal to the sample mean plus minus plus minus Z is plus minus. Okay, just let me check. Let it be Z into sigma by root n. What is Z? This, you know, this is your sample mean. This confidence interval. Z is your Z score corresponding to whatever confidence interval, you know, corresponding CI. So for example, if I want 95%, so this is 95.4, 2 sigma is 95.4. So if I give plus minus, if I want 95.4% to be my confidence interval, then I'll give plus minus 2 sigma. So my Z will be 2 here then. If I want to capture 95.4% confidence interval, so my Z will be equal to 2. If I want to capture 99.7, my Z will be equal to 3. So that is the corresponding Z score. If I want to capture 68% confidence interval, my Z will be 1 plus minus. Okay, that will be 1. This is what it captures. Sigma is the population standard deviation. So let's write it. Sigma. This is your population standard deviation, and this n is your sample size. Okay. So this is your confidence interval. I think all the concepts are clear. Now quickly let's see an application of this so that the concepts become even concrete. So let's do a question. Okay, for example, let's do a question. The question is, I have two companies and I give you salaries of two companies, and now on the basis of that salary information that I have, I ask you to determine which company is offering you a better salary. If you have two offers in hand, which one will you join? Okay, and then that analysis you have to make. So let's do it. And then now you have got the tools of statistics, and based on that knowledge that you have acquired, I think you should be able to make a better decision. Let's see. So you have to suggest to some friend, suggest which company A is better. Okay, based on the details of the salaries. So the details of the salaries, I'll give you details of the salaries based on sample size of 50, based on n equal to 50 people they surveyed, and I have two companies. Okay, so I'll give you company. Okay, and then the average salary x bar, and then I'll give you standard deviation. This you have to, okay, this information you have. So company, so there is one company A, there is one company B. One is giving you 36 lakhs, one is giving you 40 lakhs. Okay, LPA. The standard deviation for this is say 7 LPA, and for this is 14 LPA. So on the basis of this information, you have to tell me with 95% confidence interval that which is a, we'll use that tool to come to that conclusion, which pay is better. So on face value, it looks that this is way better. This is only 90% of this, right? So this B is paying better, and there is nothing to think about it. So this 40 is better, directly go for it. But when you do more maths and more statistics behind this, then you will know that this is not as good. This shows that this is 4 lakhs difference, and there's no brainer that I should go for this, assuming everything else is constant, right? Work-life balance, etc., quality of work. So let's not get into that. So let's find out. So how will we do? So we'll go for first company A. So this is called margin of error, this Z, and the Z value, the Z score. Okay, so Z score, I'll give you Z score for 95.4 was 2 standard deviation, and Z score for 95% CI, 95% is equal to 1.96. Okay, just slightly less. Okay, so with this information, let's calculate. So this is the formula, Z into sigma. So that is, this part is called margin of error. So I'll say margin of error for A, company A. This will be equal to Z into sigma by root n. N is constant for both. Z is 1.96, sigma is 7 LPA, and by square root of 50 the sample size. So this will come out to be approximately this is 7, this will also be 7, approximately 7, so this will be 1.94. okay, similarly so what will be the confidence interval for A? This will be equal to what was that? So my mean average salary x bar plus minus Z into sigma by root n. So this will be equal to, my mean is 36 plus minus 1.94. This will give me the confidence interval. So this will be 34.06 to 7.94. Okay, and then similarly for B, what will be B for B? Margin of error. Margin of error for B will be equal to Z into sigma by square root of n, that is 1.96 into 14 by square root of 50, that remains constant. So this is just a double of that, that will be 3.88. And my CI for B will be equal to x bar plus minus Z into sigma by root n, that is 40 is my average salary here, second one, yeah, plus minus 3.88. So this will come out to be, the confidence interval will be 95%, 36.12, 43.88. Okay. So 95% confidence interval for A came out to be 34 till almost 38. And this came from 36 to 43, 44. This is my 95% confidence interval based on the data that I have. You will see that there's a slight overlap. From the lower range of this, that is 36.12, to higher range of that, 37.94. These two values. So in this range, both of these companies' salaries are overlapping. So there may be a case, if you get on the lower end of this company, then you will get 36, and if you get on the higher end of this company, then you can get 38, almost 38. So you will end up getting paid more for this company than this company. So this is not outrightly that you can say that this company is paying better, because you have to consider the standard deviation also that into equation, and now you have the information of confidence interval, and the basis of this, now you will have more confidence to decide which company is paying better. I hope this helps. And now finally, what is the, why are we learning this? What is the application? Where is it used? What is the application of confidence interval? So generally, if with respect to machine learning models, okay, so instead of giving one accuracy value, okay, that it is 88% accurate or 85% accuracy for any given data, we give a better way to give that would be that I give a 95% confidence interval. Instead of giving 1 point estimate, if I go and give my manager that instead of giving that this model is performing like accuracy of 85%, accuracy of ML model is 85%. Instead of that, if I tell that with 95% confidence interval, this is this accuracy is lying between 82% and 88%. If I say this, then this is a better metric to give your manager or whoever it is. They will appreciate it better that this is giving me 95% confidence interval, and this, I don't know if you have considered outliers, etc. So this may come out to be this. Okay, so this is a better metric, more confidence. Okay, and it gives better understanding of what we have done. Similarly, when we are doing A/B testing, even in A/B testing, this is used. When we are comparing, okay, two or more versions of the product, even then we are using this confidence interval. So we'll calculate confidence intervals for each of the product, and we'll see that which product version is performing better, and that 95% confidence interval metric is better than 1 point estimate here. I hope that helps. Okay, now let's do a quick revision of what we have studied. We have studied a lot of things, and then we studied what is sample mean, what is population mean. So population mean is a true average of the entire group. Okay, that's a central tendency of the entire group. The population can be a city, a class, or the whole country. So depending upon the context, that is my entire group, and that is generally estimated using sample mean. Okay, so I use the sample mean to estimate the population mean. This is the average of a smaller, the sample is a smaller representative sample of the, or a subset for the population, and this provides the estimate for population mean, and generally we use this only because we can't go for the complete population. Okay, and we see the formula, that's simple. And then we understood law of large numbers. Law of large numbers simply says that as the number, this n becomes large, n tends to infinity, becomes large and large, this sample mean will converge to the population mean. Okay, for IID samples, that all the samples are independent, otherwise the new samples won't bring any new information, right? So assumption is that all the samples are independent, then this sample mean will converge to the true population mean. Then we went to central limit theorem, that if I have multiple samples, so this have n samples, say sample is a large sample, 100 samples, and I do this multiple times, okay, and I calculate the mean of all these trials, whatever trials I'm doing. If I calculate sample size of 100, and if I calculate the mean for each trial, and finally if I plot these means, these sample means for each sample, okay, k times, and if I plot these 1000 or 100,000 data points that we saw, then this sample means distribution will be a Gaussian with when n is greater, n is large. So generally for practical purposes, anything greater than or equal to 30 is considered as large. So for n greater than or equal to 30, this sample mean will become this will be following a Gaussian distribution, with mean will be the population mean and the variance will be sigma square by n. This is okay. The distribution sample mean will converge to a Gaussian regardless of the distribution of the population data we have. Okay, so whatever is the distribution of the original population, I don't care. Still, the means, the sample means will follow a Gaussian. Okay, that was my central limit theorem. Then we understood what is the calculation for the variance, the sigma square by n, from where this comes. We did the calculation for that, and then we found out the standard error. Standard error is sigma by, that is the square root of variance, that is sigma by root n, and the standard error is the standard deviation of the sample means. Standard deviation of the data is sigma, that observations that we had, but the standard deviation of the sample means, each mean we calculated, which is following a Gaussian, that is termed as standard error, and that is sigma by root n. Okay, then we standardized it. Standardized is mean centered and variance scaled, so everything will, the mean will become 0 and my variance will become 1. That's what mean centered variance scaled standardization means, and we'll come against this topic again and again. You will listen to standardization, and that's what I mean. Okay, and then we standardized the data, and we found that if this is standardized and as n tends to infinity, this will converge in distribution to a normal distribution with mean 0 and variance 1. And we saw this with 1000 samples, and then we calculated confidence intervals. That confidence interval is the range of values that is likely to contain our true population mean. So giving 1 point estimate, I give a range of value with the confidence interval. And what is that 95%, or what does this confidence interval mean? That, for example, if I'm talking about 95% confidence interval, which is the most common confidence interval, where, so if I take 100 samples, okay, and I calculate the confidence interval for each of them, then 95 out of 100 such confidence interval will capture my true mean, true population mean. That's what 95% confidence interval means. It is not the probability. Okay, so once we had this, okay, and then we found for the normal distribution we saw, and then we calculated that this is the formula, that sample mean plus minus, this is z score. And z score, I told that z is 1, then 68% for data, 68% confidence interval or 68% of data, this z is 1. For 95% of data, z is 2, and for 99% of the data, z is 3. And then we saw it a salary problem, comparing salaries of two companies, and we found out that what looks on paper, it is very close. And then we saw applications of confidence intervals, where we use it to report the accuracy of ML models. Instead of 1 point estimate, we give a confidence interval, and plus in A/B testing, where we are testing multiple versions of a product, there we use confidence intervals to compare the means of the how the versions are performing. I hope this is clear. That's all for this video. Thanks for watching this video. Have a good day, and bye for now.